Hi, everyone. My name is Jasper, and I'm from the University of Washington in Seattle in the United States. And I'm presenting this work on a framework for representing digital fabrication machines in computer language. And I'm presenting this work on behalf of my co-authors, Kong Lee and Nadia Peek. This late-breaking work is part of a bigger project that is still a work in progress. So digital fabrication machines have become popular research subjects lately in HCI. And digital fabrication is an umbrella term for any machine that's controlled by a computer, also known as CNC. And so one example people might be familiar with is a 3D printer. And a 3D printer takes a digital 3D model, translates the model into machine movements known as the toolpath, and then extrudes plastic while following this toolpath to get the final plastic object. And so digital fabrication technology has been around since the 1950s in factory settings, but it's only come to consumer settings in the last 2 decades. On the right is an example of a face shield holder for healthcare workers that a makerspace 3D printed at the start of the COVID-19 pandemic. And these machines span an incredible breadth of scales and applications that I can't completely cover here, but I'll give 2 examples. On the left is an image someone on Twitter posted of using their desktop plotter, which is a drawing machine, to draw a city map. And on the right is a 20-foot tall robotic arm with a specialized extruder that is casting and shaping a concrete pillar. Given this breadth of machines, it would be great to have one representation that can be used across different platforms rather than having each platform design its own representation. And this leads to our research question: how can we describe a breadth of existing digital fabrication machines in a programmatic form? And note that we want to describe rather than prescribe machine components. In designing our machine grammar, there's a trade-off we need to make in terms of level of representation. And ultimately, we went with a coarse grain approach because this will help us design a grammar that's more portable and extensible later on. To this end, we came up with an abstraction called a block. And a block represents one functional unit of a machine. A block has dimensions, width, length, and height of a bounding box. It has a position either explicitly set with XYZ coordinates or implicitly set via a connection, which I'll talk about later. And it also contains attributes, which are physical details that matter for machine kinematics or that calculating how the machine actually moves to do what it needs to do. To get a sense of how these blocks work, here's a side-by-side of the physical Prusa i3 3D printer and its representation in blocks represented in a scene. So we'll put an orange box on the left around one important part, which is the motor. And on the right, we see the motor represented as a block. This is in yellow. And we can do the same for, on the left, the blue. This is showing the crossbar mechanism, which moves the extruder. This is represented by a block on the right. And then, of course, the extruder itself, which deposits the plastic, is represented as a block on the right. So why bother making everything into neat little cubes? And one reason is that we can establish a relatively simple of how these blocks move that actually works for a wide range of machines. So here we see a block in blue that is powered by the motor in gold. And what this means is the blue block can actuate. And so the blue block is a parent that has a connection with the child block in gray. And whenever the blue block actuates, that means the gray block will start to move. And we can kind of compound this into what's called a kinematic tree. And this is a model that works for many machines, even with a simple abstraction. And for more details on this, please read the late-breaking work. So our next steps with this initial grammar are representing higher and lower level machine details, comparing and contrasting machines based on their grammars, and enforcing best practices when working with machines. And so I'd briefly like to acknowledge some people. First, Chandrakanta Nandi for feedback on the language design, Blair Subaraman and Gabrielle Ben Abdallah for evaluation and feedback, and the Alfred P. Sloan Foundation for gracious financial support for me to be able to do this work. And thank you all for listening.